This video is a review of momentum for AP Physics 1. We define momentum as the product of mass and velocity. So when mass is measured in kilograms and velocity is measured in meters per second, that means that momentum has the ugly units of kilograms times meters per second, or kilograms meters per second. So an object with a mass m and a velocity v has a linear momentum p. And now that we've studied rotation as well, we can appreciate that the quantity p, which is the product of mass times and velocity, really is linear momentum. So make sure you know that this kind of momentum is called linear momentum. And lastly, because velocity is a vector, it points in a particular direction, then momentum is also a vector, which means that if momentum points in the positive direction, then the momentum is positive, and if it points in the negative direction, the momentum is negative. And the direction of the velocity will always tell you the direction of the momentum. The conservation of linear momentum is determined by whether or not external forces are being applied to an object. So for example, if an external force is being applied to an object, then that can change the momentum. So there are a few ways that external forces might be applied to an object. First, if an object is moving along at a constant speed with a constant momentum, and I push it, that would quite obviously be an example of an external force. What we mean by external is it's external to the system. So if the object represents the system, and I push it and I'm outside the system, then I have exerted an external force on that system which changes the momentum of that object. Another example, which might be more subtle, is an object that's at the top of a ramp, and maybe we know that due to the inclined nature of this ramp, a component of the weight points down the incline. So mg sine theta, the component of the weight that points down the incline, accelerates that object down the incline. And so actually, if you look at Newton's second law for the acceleration, you would find that the acceleration, if this truly is a frictionless surface, would be equal to g sine theta. In the F equals ma equation, the two m's would cancel and the acceleration would be equal to g sine theta. In this example, we could, if we wanted to talk about it in terms of linear momentum, we could say that gravity is an external force that changes the momentum of the object as it goes down the inclined plane. Maybe you've not thought about it in that way before. But if this object is accelerating down this inclined plane, then its velocity is changing. So what's changing its velocity? Well, there's an external force, the gravitational force, which is accelerating it down the ramp. So in this case, momentum wouldn't be conserved. It would be difficult to talk about the conservation of momentum of a block going down an incline because there's an external force there. But sometimes we know some information about that external force, and we can calculate by how much the momentum is changing delta p. So delta p represents a change in momentum, and maybe we set that change in momentum equal to the force that's being exerted on the object over the time interval over which it's being exerted. And so the product F average times delta t will tell us that change in momentum. However, if the net external force is equal to 0, and so I have an object moving along with a constant velocity, the mass is constant, the velocity is constant, and there's no external forces acting on the system, so no external forces, right? The net external force is 0, then that means linear momentum is conserved. And the idea of linear momentum conservation is really important in physics because it's one of our conservation laws that allows us to solve problems. And the way that we write conservation of linear momentum equations is we typically will write pi equals pf. We will set the initial linear momentum equal to the final linear momentum. And of course what that means in principle is that the change in momentum is 0. And maybe it makes sense comparing this to the equation at the top, right? Because if the average force is 0, then the change in momentum would be 0 as given by the top equation. So of course the initial momentum and the final momentum will be equal. And this most often happens in types of collisions. An object will collide with one another. Maybe the mass and velocities are exchanged or changed around a little bit, but the momentum is conserved. Because when I'm dealing with a collision, say between two carts, where one cart is moving to the right and the other cart is moving to the left, they can collide, but as long as the two carts are both part of the system that I'm accounting for in my conservation of momentum equation, then the forces that those carts exert on one another are internal forces, and internal forces can't change the momentum of a system. Let's look a little bit further at this equation which relates the change in momentum to the average force in the time interval. So let's think about what practically happens when one object it has a force being exerted on it. So first let's talk about this sentence that I have written at the top. When a collision occurs, the force is variable. So let's take, for example, maybe we just have an object that is being thrown against a wall, or maybe it's about to bounce off the floor. When that object hits the floor or the wall, the force that the wall exerts on the ball is variable. And we see that because when the ball hits the ground, initially it will just come into contact, and then eventually the ball will become deformed quite a bit. Maybe it squishes down to half its original size, and then eventually it'll shoot back up. And so at that point of maximum compression, right, maximum compression, that would be the case where the largest force is being acted upon that ball. But clearly the force is exerted over some time interval at all moments when the ball is in contact with the floor. And the way that this would look is, if I put a little mat on the floor that could measure the force, imagine a mat that, has some area to it. It looks like a little square, and I drop a ball onto it, and it can measure the force that the ball exerts as a function of time. Then the graph might look something like what I have on the left. As the ball comes into contact, the force exerted on that mat starts to increase up to a maximum point, where at this point that would be the place where the ball is compressed the most, and then as it starts to get decompressed and then shoot back up into the air, the force will decrease again. So clearly this collision occurs over some time interval delta t, and the force is variable. So there's a maximum force here, right? But the force that would go into this equation up above is the average force. So one way to calculate the average force is maybe by looking at this graph and finding some point that's kind of like in the middle. And depending on the shape of the graph, you may or may not be able to determine that average force by looking at the graph. But more often than not, the way that we're going to find the change in momentum from a graph of force versus time like this is we're going to calculate the area under the curve. So delta P, as I have written in green there, is going to be equal to the area under the curve of that graph. And one way you can really make sure that you're remembering that is let's imagine a little square inside of this area. That square has a certain amount of area. And think about the height of that little square. The height of that square would be equal to some amount of force, and the width of that square would be equal to some amount of time. And so the area of the square would be its length times its width, or its height times its whatever, and that would be force times time, and force times time equals change in momentum. So if I had a way of calculating the entire area under that curve, I could find the change in momentum of an object. And the reason why that's important is because more often than not, in a graph like that, we'll get a graph that looks like the shape of a triangle or maybe a square, and so it's pretty easy to use area equations like 1/2 base times height, for example, for a triangle, to calculate the area under the curve. And then we'll know the change in momentum. Another way that we get some information from a graph to solve a momentum problem is from a position versus time graph. Because inherently, if I'm calculating a change in momentum, in the first graph I could get that by using the force versus time graph, but sometimes I can directly calculate PF minus PI from the graph given. And that's especially true for a position versus time graph. So say I told you in a problem statement that an object has a certain amount of mass, so you know what the mass is, and that could be plugged into these initial and final momentum terms. All you would need to know is the velocity before and after the collision in order to determine the change in momentum. In most position versus time graphs, the collision is very identifiable because when the collision happens, there's going to be a change in the velocity. And so here, that collision happens right there. And before that, there is some slope that is very identifiable, and the slope of a position versus time graph tells me the velocity. Not only the speed, but the velocity. And here it's a positive slope, so that would correspond to a positive velocity that I could use with the mass in my change in momentum equation. And then after the collision, not only has the speed changed, but the velocity changes. The slope now is negative, and so that negative speed could be used in my momentum equation to find the change in momentum. So it's really important that we remember that momentum is a vector because velocity is a vector. And so if I'm pulling information from a graph, I need to account for whether or not the momentum is positive or negative. And something that students run into a lot is we see this minus sign here. That minus sign in the delta P equals PF minus PI equation is not a minus sign that means the initial momentum is negative, and it's not a minus sign that has anything to do with the directionality of anything in the problem. Delta anything is final minus initial. So if, for example, the initial momentum is negative, I have to plug in another negative sign into the initial momentum in order to account for that direction, not that minus sign. And lastly, a point that I want to make at this juncture about the area under a force versus position graph or a force versus displacement graph is that the force versus position graphs that we've seen, the area under those graphs represents the amount of work being done on an object. So please remember that if I have a graph of force versus force versus time, as I have in the upper left-hand corner, then the area under that curve is the change in momentum. And if as I have down below, if I have a force versus position graph, the area under that graph represents the work being done. The main thing we studied with linear momentum were different types of collisions. So first I'd like to say, as I have at the very top, that momentum is conserved. Linear momentum is conserved in all collisions, okay, as long as the net external force is equal to 0. So in those cases, all collisions have momentum being conserved. In general, there are two classes of collisions. There are inelastic collisions and elastic collisions. So we'll start on the left-hand side for elastic collisions. Elastic collisions occur when two objects collide and move separately. So one collides with the other, and then after the collision they're not stuck together. In those types of collisions, energy is conserved, right? So what that means is the kinetic energy at the beginning, before the collision, and the kinetic energy after the collision can be set equal to one another. And remember, kinetic energy is 1/2 mv squared. So we're essentially saying I can write 1/2 mv initial squared equals 1/2 mv final squared. And remember, for collisions, there could be two or more objects that are colliding, and so maybe each one of those things independently has its own little kinetic energy, and each one of those would have its own independent term. For example, if before the collision two objects are moving, I might have 1/2 v initial squared for one of those objects, 1/2 v initial squared for another object. In general, I have a little initial and final case down below for the elastic collisions. let's say that m2 is at rest, its velocity is equal to 0, but m1 is coming along with some velocity v. I know that if this is an elastic collision, then that means both the momentum and the energy are going to be conserved. But what the picture looks like for the final case depends on the ratio of the masses. So I have three cases that I need you to remember. The first case is where mass number 1 equals mass number 2. If that's true, then what will happen is m1 will stop and m2 will continue to move forward at a speed v. So you can think of this as all of the momentum that the first object has is being delivered to the second object. So one stops in place and the other moves off with the same speed, as long as they have the same mass. The second case, m1 is greater than m2. In this case, it's tempting to think that m1 will kind of just plow over m2 and carry it with it, but remember, these two objects have to move separately. They're not sticking together. And so for that reason, if m1 is greater than m2 and they don't stick together, then what happens is m1 and m2 will both end up moving forward after the collision, which here means to the right, but they'll just have separate speeds. Typically, the second object, being lighter, will get hit and move a little bit faster, and then m1 will be moving a little bit slower behind it. And the third case is where the object that's at rest, m2, is actually heavier than m1. And in this case, although m2 is heavier, when m1 comes along and hits it, m2 will be moving to the right ever so slightly, probably not very fast. So m2 will go forward, and m1 will recoil back in the negative direction. So especially in this case, where m1 recoils backwards, you would have to account for that momentum in your equation by writing a final amount of momentum that would be negative for object number 1. In each of those cases, the momentum has to add up to be equal in the initial and final cases. And now let's move over to the inelastic collision case. Inelastic collisions occur when two objects collide and energy is not conserved. So if energy is not conserved, the collision is inelastic. And so two objects can collide and they don't necessarily stick together, but there's lots of energy losses. So for example, more often than not, when two cars collide with one another, they don't necessarily stick together, but the bumpers get all bent and there's lots of energy loss. I hear the crash between the two cars, which means there's lots of sound energy. There's probably braking that happens where the cars slam on their brakes, and there's some heat exchanges with the tires in the road. And so there's all sorts of energy loss, but the cars don't necessarily have to stick together. Those would still be inelastic collisions. However, if they do stick together, we call that a perfectly inelastic or completely inelastic or totally inelastic collision. Any case where they're sticking together, we would give it that name. And so in particular, if two objects are sticking together, I've got a picture of this collision happening. So the initial case, maybe one object is at rest and the other object is moving along with the speed v. They stick together. And when they stick together, the mass of the stuff that's moving becomes 2m. And you can see that in the picture right now. Now it's become 2m. Initially, only an object with mass m was moving. Now that same amount of momentum has to push 2 units of mass. And so you should expect that the speed goes down. And down below, I have a conservation of momentum equation, which says initially the momentum is mass times v initial. So that's my initial speed that the object had. And then the final mass, or sorry, the final momentum is the mass of the two objects added up together, m plus m, times the final velocity, v final. And in this case, if I didn't know what that was, I could just write v final. But by comparing the two sides of this equation, I can add up the m plus m, I get 2m, and I could solve for vf, and I would find that the final speed would be equal to 1/2 the initial speed. And so in problems where two objects are sticking together, it's pretty easy to account for that final speed. We just say that if the mass increases by a certain amount, the speed has to decrease by that same amount. And so there's a relationship there that we can kind of understand, maybe even qualitatively or semi-quantitatively, without having to worry about the equations too much. In general, remember that there's two types of collisions, elastic and inelastic. As long as the net external force is equal to 0, the momentum will be conserved, and only when the objects collide elastically is the energy also conserved. And so sometimes you have to worry about whether one mass is greater than the other for the elastic collisions. But inelastic collisions, the objects stick together, and it's a little bit easier to consider what the final result of the collision will be. Lastly, a few final things that I think are important to remember. First, the velocity of the center of mass, right? And hopefully you remember what I'm about to say before I even say it or before looking at the screen. The velocity of the center of mass is constant as long as the net external force is equal to 0. Think about this, right? Some objects are moving along and they have a certain velocity. The net force exerted on those objects is 0, so the velocity is constant. This makes total sense because in order for an object to change its velocity, there has to be a force present in the first place, right, by Newton's second law. The reason why the velocity of center of mass stuff tends to be a little bit complicated sometimes is because when I'm working with complicated systems. For example, we've seen a system where there was a little cart connected by a spring to another little cart. And because of the way that they were connected, there was a little band across the top, and they were put on a frictionless track. So you can imagine these objects being placed on a track that is frictionless, where maybe the whole system is moving to the right. And what we saw was that if you give the carts a little push, the spring extends and then compresses, extends and then compresses. So actually what happens is one of those carts moves and then the other one catches up, and then the other cart moves and then the other one catches up. So it has this really irregular kind of motion. But then we saw in a video that if I turn off all the lights and the only thing I can see is this dot in the middle, that by watching that dot, it moves at a constant speed to the right. And the reason for that is, once I give those things a push, they're moving along with a constant speed on this frictionless air track. And there's no external forces. The spring forces and the forces that the carts exert on one another, those are all internal forces which can't change the velocity of the center of mass. Therefore, it's constant. Another point, we tend to talk about all these collisions as being carts coming from the left and coming from the right, sticking together or whatnot, but conservation of momentum is very often going to be applied in situations where there's an explosion. So if there's an explosion, maybe on the right here my picture of this little red thing is like a little pipe or something like that that has some explosives inside. And so that pipe is maybe just resting on a shelf or something like that. And the initial momentum is 0 because there's nothing moving, right? After the explosion goes off inside the pipe, maybe the pipe splits into two pieces. One moves to the left and one moves to the right. And there's momentum now. Each of those pieces independently has momentum in a different direction. But because the momentum before the explosion was equal to 0, the momentum after the explosion also has to be equal to 0. So despite objects moving, the momentum is still 0. And that's because, if momentum is a vector, to the right maybe that's a positive amount of momentum, and to the left maybe that's a negative amount of momentum, and those two things added together would produce 0. So make sure you know that momentum can be used in the case of an explosion as well. Also, Newton's second law can be written as F equals ma, and acceleration can be written as delta v over delta t, and hopefully you see that mass times delta v is the same as a change in velocity, right? M delta v is delta p. And for that reason, Newton's second law can be written as delta p over delta t, or the time rate of change in the momentum. which rearranged is exactly the equation that we've been staring at earlier, right? F delta t equals delta p. Lastly, a comment that I made earlier is the idea that internal forces cannot change the momentum of an object, right? Only external forces. And hopefully you remember the picture of, or not the picture, but the video of that truck that was stuck in the mud where, well, this is a beautiful little truck. There was a truck stuck in the mud, and there were a bunch of people trying to move it, and there were people standing behind the truck that were pushing forward. They're capable of applying an external force to cause the truck to move forward, to change its momentum. But then there was an example where a part of the video where the person was on the back of the truck, inside the truck, trying to push forward on the truck. And of course, we know that the person inside the truck, on the back of the truck, is not capable of pushing the truck forward because they are internal. They are on the truck. They are part of the truck system. Therefore, there's no way that they could possibly move that truck forward. So remember that only external forces can change the momentum of an object.